Rolling bearings are made so that the wheels of industry can turn with the least possible resistance. Some are being manufactured to turn at 250,000 revolutions a minute. Others are being manufactured to revolve at only 1/4 of a revolution a minute. In the manufacture of all components of a bearing, precision is the keynote. Equal care is also needed in the assembly of bearings, whether they will eventually carry loads of many tons or just a few ounces. Bearings are assembled for use in different conditions, in water, in dust, and in extreme temperatures. In fact, bearings constitute a world of precision engineering, on which the wider world of industry turns. The rolling bearing in both the ball and roller form has many variations, but the ball journal bearing is the most widely used. The inner ring fits onto a shaft. The outer ring usually fits into a housing. Steel balls form the rolling elements. They are separated from each other by a cage. Cages are made to center either on the rolling elements or on the inner ring, and occasionally on the outer ring. In the ball journal bearing, the rolling elements run in the raceways formed in the rings. This type of bearing can carry a high radial load, a moderate axial thrust, or a combination of the two. A typical application is an industrial gearbox. The loads are transmitted from the gears through the shaft and so to the bearing. For ease of assembly when installing some bearings, the outer ring is made so that it can be separated from the rest of the bearing. When the radial load is beyond the capacity of the ball elements, rollers are used, which carry the load over a greater contact area. A roller bearing of the same external dimensions as a ball bearing carries far greater loads. There are many applications for roller bearings in heavy industry. When a roller bearing has lips on both rings, it can also carry axial thrust, provided the thrust is not continuous and the speed is not too high. A variation of the standard roller bearing is the needle roller bearing, especially suitable for oscillating motion. An example can be found in the balance beam of a lorry's suspension. At slow speeds, the needle roller can carry heavy loads. Fewer needles are used for higher speeds, but they are caged. Needle roller bearings are smaller in diameter than normal roller bearings, and are useful where housing diameters must be limited. Needle rollers can be used without the inner ring, but the rollers must then run on a hardened shaft. Just as the roller bearing has its variations, so does the ball bearing. If a ball bearing is to carry a substantial axial thrust, either with or without radial loading, the ring profile is altered. A larger clearance is provided between the rolling elements and the raceways, resulting in a greater angle of contact. The outer ring of the angular contact bearing is cut back so that more balls can be fitted. The bearing is now able to carry the heavy axial thrust found in heavy drilling operations. Where the axial thrust is greater than the capacity of the single angular contact bearing, two bearings can be provided in a tandem mounting. Alternating axial thrust is met by back-to-back or face-to-face mountings. Another method of meeting alternating axial thrust is the duplex bearing, which has an inner or an outer split ring. The extra capacity of the duplex bearing makes it suitable for the heavy axial thrust in machinery like vertical pumps. Where the load is too great even for the angular contact bearing, the tapered roller bearing is used. As in the case of angular contact bearings, tapered roller bearings may be mounted face-to-face to take alternating axial thrust, or more usually back-to-back. These bearings are fitted to car wheel hubs. Cornering adds heavy axial thrust to the radial load. Where there is no radial loading, a bearing designed to carry only axial thrust is used. One example is the bearing at the pivot mounting of a swing bridge. All the different bearings examined up to now have been of rigid design. That is, their use required the bearing housing and shaft to be in alignment. But sometimes, housings may not be in line. So the bearings are made self-aligning. The raceway is formed spherically and two rows of balls are inserted, or two rows of spherical rollers. Externally aligning bearings are journal bearings with a spherically formed outer ring, free to tilt in a matching housing. Self-aligning and externally aligning bearings are used in machines where alignment cannot be guaranteed. This completes the general picture of design, but there are many modifications of all the types of bearings depending upon their applications. The uses of bearings are so various, so numerous, that each type is manufactured in several hundred different sizes. All the skill in engineering design will not, however, make rolling bearings completely frictionless. Bearings must be lubricated. Even under the lightest load, both the rolling elements and raceways undergo microscopic changes in shape. Areas of contact occur, and there may be some relative sliding between the rolling elements and raceways. The rolling elements also rub against the cage. And some designs of cage rub against the inner or outer ring. At all these areas of contact, excessive friction, heating, and heavy wear would occur unless a suitable lubricant is used. Whether it is grease or oil depends mainly on the combination of size of bearing, speed, load, temperature, and moisture. The effect of two of these factors on the selection of the lubricant is shown by plotting size of bearing against speed. At At light loads and normal temperatures, in the area above the curve, oil would normally be used. And below the curve, grease. In fact, grease is used in most applications where speeds and temperatures are normal. It is easily retained in the housing, prevents corrosion, and helps to stop dust and moisture getting in. Where speeds and temperatures are high, oil is used because it dissipates heat more readily and offers less frictional resistance. Oil is also used where high temperatures and heavy loads occur together. The oil that lubricates the machine often lubricates the bearing. For high temperatures, and particularly for high speeds, oil mist lubrication is applied by passing compressed air through a venturi, drawing oil from the bowl. Part of the oil is atomized and is carried by the air to the bearing. This system is especially suitable for grinding machinery, where in addition to lubricating and cooling, it also helps to prevent metallic dust entering the bearing. Whether used in heavy or light industry, rolling bearings must work with precision and reliability. And for this, they depend to a large extent on efficient lubrication.